Recall last time in video 4 that we made a density of states argument for the number of electrons in the deuteron intermediate state, D2 star. Let's briefly look at this from a chemist's perspective. The palladium crystal with the two deuterons is our molecule. Here we start with the deuterons in the beta crystalline position. Then we let chemistry work and form molecular D2. Then, if everything is right, this can form the D2 star intermediate for a small fraction of the time. The deuterons in the D2 star state have an orbital energy of about 300 electron volts. This momentum, or angular momentum, is taken from the conduction band electrons that participate in the D2 star state. We show here how the diffracted electron transfers its momentum to the deuterons, and when the deuteron moves a little, a new electron state must be diffracted while the other state moves on. We'll give an example of how the state moves on in a minute. So obviously, we need enough electron states to go with the deuteron positions. This is all a density of states formulation is doing. So to repeat, as each electron is diffracted, the electron state is localized and no longer contributes to electron concentration elsewhere. Of course, since there are over 220,000 electrons involved in a D2 star, each electron has less than a 10 to the minus fourth probability of being in the D2 star state. Here we show the deuteron orbital radius and the average electron momentum and radius given to the deuterons. This does not mean that the electron interacts from several nanometers away. It is a manifestation of the D2 star as a diffracted state which does not alter the overall energy of the conduction band electrons. When the D2 star state forms, some of the probability of all the local conduction band states must be involved, as we will show in a minute. The electron concentration in this state originates from the electrons elevated from the molecular deuterium up into the conduction band. Before we move on, I want to show a simple real-life example of how an electron can interact with the potential and not be affected outside of the potential. Here we show an electron approaching a spherical constant potential. We draw the potential below and fill in the lowest ground state. Now we draw the energy level of the free electron so that it is above the outside potential. This just means it is a free electron. Now we draw the wave function of the free particle as if there were no potential. Then we draw in the wave function of the electron with the potential and see that it exactly matches the free particle wave function outside the potential. This means the electron acts as if the potential were not there. The potential is transparent at this electron energy. This is called the Ramsauer-Townsend effect and was discovered almost 100 years ago using electrons diffracting from the inert elements. A question troubling some may be why molecular D2 is analyzed differently than the D2 star intermediate. The answer is fairly simple. With molecular D2, the electron can complete an orbit while the deuteron moves less than a nuclear diameter. The electron distribution does not change much with each orbital time period. In the deuteron intermediate, the deuterons have 3 orders of magnitude more orbital energy, about 300 eV, and the electron wave function is very restricted in diameter. For one oscillation of the electron up and down is shown, the deuteron moves enough to be outside of much of the electron distribution. This means the Born-Oppenheimer approximation cannot be used for the orbital dimension of the electron. Instead, we can use Feynman's integral wave equation, which takes account of the full deuteron orbital time. This means we will need to describe the electron behavior as it oscillates back and forth between the deuterons in a corkscrew fashion while turning with the deuterons, sort of as shown. Fortunately, the energy of the electron associated with the turning deuterons is very small and can be neglected to good accuracy. We simplify the problem by concentrating on one point along the z-axis aligned with the deuterons. We want to visualize what the electron orbit at this point looks like throughout the deuteron orbit. So we draw in the orbit of the electron following the deuteron as shown, then draw in the local orbital motion of the electron in the parabolic potential we discussed before. Now we sketch in the local orbits as the deuterons turn. We want to find the time-dependent behavior of the electrons, so we label the start TA and the completed deuteron orbit TB, and draw a graph to show the complex part of the electron phase factor. And we luckily chose a point that perfectly repeats and would be a stationary state. We call this point radius r, and choose another point of slightly smaller r, say r prime. This r prime will have a different force constant for the parabolic potential, and we see that it no longer fits exactly in the deuteron orbital time. This orbit would not be stationary. We need to take a closer look at the oscillation frequency along the z-axis, which is a function of the force constant, which changes continuously along the axis. We start by drawing a graph of the frequency, a function of the force constant, versus the time-dependent phase factor. We know the time, Tb minus Ta, from calculating the deuteron wave functions. And the energy, E, is just frequency times Planck's constant. But we leave it as energy E, a function of Z. Obvious, this creates a straight line. We now choose a phase factor equal to an integral number of 2 pi, call it n times 2 pi, and draw in n plus 1, n plus 2, and n plus 3 times 2 pi. As we saw previously, only these points will be stationary. All the in-between points will not give a stationary state. So now what? Well, what if we can cheat and put in a variable fudge factor, energy called E sub f, energy fudge factor? Then, how big does this fudge factor need to be? The fudge factor times the deuteron orbital time divided by Planck's constant needs to range from 0 to 2 pi. This would allow all the electron z positions to be stationary. The E sub f turns out to be the Fermi energy. This fudge factor is just the range of energies in the conduction band, which will make this diffraction state a stationary state. So we see that the essentially continuous energy states of the conduction band will make the intermediate state a stationary time-independent state. Who knew? The physical properties required for this state is a spherical set of conduction band states with a Fermi level of about 10 eV. This will not be the Fermi energy, but the minimum energy of the Fermi surface, which is a set of states of maximum energies in all directions. This is probably one of the critical physical factors required for cold fusion. This full three-dimensional set of plane waves will then be essential to the description of the deuteron intermediate state. We should probably mention the role of identical particles. The conduction band electrons all occupy the same space, and electrons of the same spin are identical. This means that the description of the electron, the wave function, must consider each electron as being in every state in every permutation of the electrons. This gives the uncertainty of the electron band energy needed to complete the formal calculation of the deuteron intermediate state. Now that we have some basic background, albeit confusing, we will start next time with the derivation of the equations required to make the calculations to describe the fusion reaction. We will start with Feynman's integral wave equation, which will quickly simplify to mostly Schrödinger equations, very similar to the molecular D2 analysis. A familiarity with differential equations is pretty much required. All of the solutions, however, are numerical, so the difficult analytical forms are avoided. With a solver program, the calculations are fairly easy, although tedious. The goal is to show how straightforward the idea is in numerical detail using time-tested and accepted concepts.